Okay, hi BC Calculus, how are you? I know that you are in class right now with Mr. Fullars, and I'm home with a sick kid. And so, what I'm doing today, actually, timing wise, is perfect because your only homework was the take home, which I know you all handed in this morning already. And so, I'm just going to jump right into our kind of lesson of the day, if you will. Um, and as I'm getting set up here, you can kind of just take down what I have here. I just have a function f of x is x squared plus 1. Then I want you to shade the region bounded by f of x, y equals 0, x equals 1, and x equals 4. And as you're doing this, you're going to listen here with one ear. What we're getting into here, AB, those of you who are from AB, we're going to get into solids of revolution, okay? As I've been saying all fall here, I think this is a place where you can really strengthen and fortify some ideas. I know there are a couple of ideas and concepts that I really emphasize, and maybe you can make particular note of that. I'm also going to talk not only about volumes here, but I'm going to kind of revisit the integral in general and kind of the real story behind the integral and the operation and the really important ideas behind the integral. And these are ideas that have kind of woven their way into our conversations in class, but I want to reinforce them here because this will hopefully be I can't say third, fourth, I think it's maybe the fifth, sixth, seventh tie-in to the idea of integral calculus that we are embarking on this year. Okay, so let me catch up with you. So you have shaded in the region x equals 1. So here's x equals 1, x equals 4, and my scale may not be perfect, and y equals 0, of course, is the x-axis, and I'm just going to go and shade this region. And I'll do this, and when I shade that region, and if I had Bennett here, I would say, Bennett, what's a really nice way to shade a region really neatly? He has the expert iPad. There we go. How's that, Bennett? Pretty good? All right. Now, here's what's important. Notice something here. I purposely set up this exercise here with us shading the region. Now, why am I emphasizing this? Well, let's see. I made a big deal of saying shade this region, right? And here's why. We are now going to revolve this region about the x-axis. Now, what does it mean to revolve a region about the x-axis? Well, what we're thinking about here is as we revolve this region, think of this as this kind of yellow piece of paper, and we're going to revolve around the x-axis. Sometimes you'll have the denotation like this, like, the axis of revolution will have this kind of rotational icon around it. As this piece of yellow paper spins around the x-axis, you will notice it occupies a three-dimensional space. And it occupies a three-dimensional space, and maybe I'll have you kind of talk about what kind of volume that space describes. What kind of volume that space describes? Well, actually, sometimes those of us who are not particularly artistically inclined will have a hard time visualizing it. But if you look here, and you obviously don't have to copy this down, but this is a visual I just clipped and snipped from the internet. This here, of course, is my function f of x, right? Ignore, of course, these x values because they chose different x values in the picture, but I think I chose from 1 to 4, right? So here's x equals 1, here's x equals 4. And you'll see that they do a very good job of rendering this solid. This is called a solid of revolution. And a solid of revolution means exactly what it sounds like. It's a solid that is the result of an area being rotated. Why do I emphasize area? Well, let's go back. If I hadn't revolved an area and instead all I revolved was the curve, everyone, and this is an important distinction because we'll talk about this too later on in the fall. If we just revolved the curve and not the area, if we just revolved the curve and not the area, what we'd have is just then the surface of this. Someone once told me this looks like a, what did they say? It looked like the top of a, I don't know, like a footstool. I've never seen a footstool, or a lampshade. That's what it was, a lampshade. They said it was like a lampshade. Like if you put the lamp here, and here's the lamp stand, and of course the light bulb will be up here. Right? Okay, but anyway, I digress. So if we just revolved the curve, then we would literally have not a volume, we'd have a surface. We'd have just the lampshade, so to speak. We wouldn't have the volume inside. And the result there would not be a volume of revolution, it'd be a surface of revolution. So right now, our task today is to revolve not just the curve, we are revolving the area. Okay, I'll just call this area of region R if you want to, all right? And when you revolve the area, you'll notice you get a solid of revolution. So let's just make a note here. When we revolve this region about the x-axis, okay, the result is called a solid of revolution. And I really like that distinction. I mean, I really like emphasizing the fact that we're talking about solids of revolution, because solids of revolution come from areas that are revolved. Surfaces of revolution are a result of curves being revolved. Very important distinction. All right. Now I'm going to go back to this nice drawing here. It's nice for me to kind of see this. This gives me a nice visual. It's kind of the solid of revolution is like it's like a lampshade that's completely filled with like liquid concrete, I guess. So basically a completely useless lampshade. But the solid of revolution is this entity. And notice right here, this here, you will notice, is a circular cross-section. And you'll notice here, and again, just right now when I'm on this picture, just listen for a minute because we're going to go back to our rendering, because the ease of these questions really is your ability to render this and have a graphical image. In this particular case, this solid of revolution is composed of circular cross-sections. Again, ignore this for right now. And if I were to ask you how many cross-sections are in this solid, I think you'd agree that there are infinite circular cross-sections. I mean, they are kind of like this. I'll draw one. Okay. I'll draw one up here. I mean, they're just stacked up, right? Circular cross sections. And of course, a circular cross section, I always want to kind of graphically make note of any critical body parts of a circular cross section. And for a circle, the critical body parts are its center. And I think you'd also agree that the critical body parts are its radius. All right, let's go back to our drawing here. So here's where I'm meeting you, and my drawing is going to be at least as, well, no, I should say at most as good as your rendering, because pencil makes this easier. At most, it's as good as yours. At worst, it is far worse. But what we're going to try and do here is attempt to draw this solid revolution. So taking your pencil, if I take this area here and revolve around the x-axis, what I'm going to get is a solid that looks like this. And we do our best, but I'll tell you, those of you in AB can agree or disagree, but I will tell you that the 30 seconds it takes you to graph this and kind of make a picture will save you time in calculus and algebra errors moving forward. Money back guarantee. What I want to do here is, let's see, I'm going to try and three-dimensionally show that these are in fact circular cross sections. Here I'm drawing a few. Okay. And maybe I'll take it all the way down. As you'll notice, when I make this picture, it looks worthy of, well, I don't know, worthy of some mild indigestion. Maybe it gives you some heart palpitations, particularly if you're artistically inclined as you watch me do this. Maybe you think that I'm actually doing something terribly horrible. Because yes, I'm not, Miss Yem is not an artist. But you can see what I'm trying to convey here is my visual of what the solid is, okay? I made a big deal about talking about circular cross-sections and making sure I emphasize and show and label critical body parts. And for a circular cross-section, those are its center and its radius. And if I'm just going to pick one of these circular cross-sections, the center of all of these cross-sections, not only that one I just highlighted or I made a center on, the center you'll notice is on the x-axis. And the radius of the circle, of each circle, I could draw the radius down to the image of the rotation, or I could draw the radius, that critical body part, up to the original curve. I'm going to make your life easier and give you a tip. When you draw the critical body parts of these cross sections of solids of revolutions, and the only cross section we have right now is the circle one, right? Draw those critical body parts to the original curve, not to its image. It will help you in the steps to come. Okay, now what I'm going to do here is just kind of emphasize this one circular cross section. Okay, and if you're someone who's a purist and you want to kind of go shade and add more three-dimensionality, you can certainly do that. If I were to ask you then to take this circular cross section and then let me do there. So I'm just kind of pulling this circular cross section out here for a minute. Okay, let's generate over here to the side an expression for the area of this circular cross section. And in calculus speak, we can certainly call this a circular cross section, but in calculus speak, this is called a disk. Okay, this shape is referred to as a disk. Well, the area of a circular cross-section, well, the area of a circle in general is just pi r squared. Would you agree? Okay. Well, the area of this circular cross-section, I'm noticing again, I'm asking myself, what is the radius? The radius is from the x-axis up to a point on the function, right? Any cross-section we look at, the radius is from the point on the x-axis up to a point on the function. So I think it's fair to say that the radius here is, what is the radius? Well, let's see. This curve was x squared plus 1. That makes the radius, or this y distance, right? This varying y distance, that radius is x squared plus 1. So the area of each circular cross-section is going to be pi times the radius. And what's the radius again? I just lost it. There it is. The radius is x squared plus 1 squared. Okay, so here's what I have now. I have my volume of revolution. I've visualized it in my head. Well, in this case, this is our first time we visualized it with the aid of this perfect computer rendering here. I've drawn it, I've drawn the cross-section, I've drawn the critical body parts, and I now have an area for a circular cross-section at some value x, right? So this makes sense that the radius here varies depending on x, because x could be any value between 1 and 4 after all, right? Those were my limits of integration. Oops, I'm getting ahead of myself. That was the interval of x over which this area and this solid exists. Okay, now what I want to do is this very important idea. I want to take the sum of all the let me pause. Okay, I want to find the sum of all my, I just made a mistake here. This should be not in. Sum of all the circles cross sections.
Are you going to go triangle by chance?
Yes, I have to get Tyler chicken noodle soup. He doesn't feel well. Sum of all of them. Okay, hang on. I'm talking to my husband. So the sum of all the circles cross sections, well, all of them. When I say all of them, how many circular cross sections are there in this solid? And I think you'd probably see where I'm going. The number of cross sections in this solid are infinite. There are infinite numbers of circles.
And this is more of an idea, right? I mean, it's an important idea because we're thinking about the slices inherent in this solid that is non-finite, it is infinite. And we wish there was a way that we could add up infinite things. We wish there was a way that we could add up infinite entities. And luckily we have the definite integral, okay? We have a definite integral, and we want to add up infinite entities. And those entities in this case are circular areas. And if we didn't have the definite integral, we would be stuck at this step right here, which is how do we describe the sum of infinite entities? Well, here it is. And I think I'm going to go through this fairly quickly, but then I'm going to bring us back to something old and hopefully familiar. I'm adding up infinite circles areas. So I want to add up infinite circles areas. This here becomes my integrand. It is my integrand because that is the thing that we have infinite numbers of. Okay, I'll say that again. This circular area expression is exactly what we are adding up infinite number of. Okay, so this becomes my integrand. Oops, I was too fast. I put the dummy so quickly, okay? But I want to make sure we understand why the dummy is that. So this is the things that we have infinite of. We have infinite circular areas. That becomes my integrand. The integrand, as we know, is the thing that we have infinite things of. And I'll go back and remind you of that in a moment, like in 30 seconds. You'll notice that my integrand here is in terms of x. What does that mean about my dummy? The dummy has to be dx. The dummy has to agree with the independent variable of your integrand. The dummy also has to agree with the limits of integration. Well, let's think about this. These circular areas exist over what interval of x? Let's go back and review. The interval of x is from x equals 1 to x equals 4. So here is my full integral expression. So at the end of the day, you know, it's always, I find it just easier in the end when you go through the exercise of evaluating the definite integral to pull the constant through. This expression here then describes the volume of the solid of revolution. And there you go. So I just said something very important, and I worry that it kind of got lost in the ether, that digital air that's separating us today. But when we did this, everyone, back in the day, and hopefully you'll remember Riemann sums, okay? And we had the classic question that looks like this, A to B. And again, don't copy this stuff down right here. This is just me kind of taking you down memory lane, hopefully reminding you of a very important journey we've been on together. The first thing we ever did was we looked at rectangular subintervals. And just arbitrarily, I picked right endpoints of each subinterval. And I crafted rectangles. And we did this. Right? And we went and figured out the width of each rectangle, the height, and we added them up, and we recognized that as the number of subintervals, we recognize that geometrically the rectangles, as an abstract idea, approached lines. Okay, I'm putting this into quotes because obviously a line is not a rectangle, but the idea was geometrically those rectangles, the delta x here became so small and approached 0 that those rectangles morphed into lines. And we saw that the rectangles, again, don't write any of this down, this is just a walk down memory lane. The area of a rectangle was delta x times the height, right? Width times height, width times height, width times height. Well, if you think about it, if a rectangle's area is delta x times height, okay, I want you to go with me here, then a line's area, if you will, is delta x times height, but delta x is really what? If you have a line, it's just 0, okay? And this height, we know the height is gotten by some function value, right? Because it's the vertical space from the x-axis of the function. So in both of these cases, it's delta x times f of x, 0 times f of x, right, if you will. But again, the idea here is that delta x is approaching 0. Delta x is approaching 0. So the idea is that delta x approaches 0. And so it's not really that we're multiplying 0 times f of x, because 0 times f of x, as you know, I think we all agree, is that 0 times f of x would actually equal 0. But it's really the area of a line, so to speak, is delta x approaching 0. Okay? And luckily, we have a notation that means precisely delta x approaching 0. Now, this is new for all of you, I think. AB, I think it is. I'm not sure if you talked about this last year or not. But we could write delta x approaching 0, but delta x approaching 0 means the same thing as dx. Okay, so delta x approaching 0 means the same thing as dx. So again, staying with this theme or this idea, this very wacky idea of an area of a line, really the area of my line is dx times the height, right? But we just said dx was the function, so dx times f of x. And now we know, let's think about this. We know how to find the value of this area here. And I should actually say net signed area, right, everyone? Because net signed area is how we understand the definite integral. But in this case, if I'm looking at the interval from A to B, the net signed area here happens to be the actual area, right? So we know that if I find that area, this area here, what do we say it is? The area equals the definite integral from A to B of f of x dx. Now, look at something. Look at this and look at this. They are the same thing. So I want you to kind of link two ideas, that the integrand here is also the thing that we are adding up infinite things of. The thing here is infinite areas of lines, right? So this here, the integrand here is, if you want to kind of think about this, it's an area of a line. And we're adding up infinite areas of lines. Here, we're adding up infinite what? Infinite areas of circles. See that? So it's really interesting. I mean, if you really have, I think, this whole idea down here, you didn't have to copy it down, but there's a difference between doing the calculus and really understanding the story behind the calculus and why calculus is written and talked about and solved the way that we do. This here really gets at it, particularly this idea right here. Some of us just throw dx around or our integrands all over the place, never really fully understanding what dx actually means, okay? I'm gonna go back up to here by visual. Here is another rendering of this solid that we're working with. And you'll see here, really, that each of these cross sections, see how we have a little bit of thickness, right? We have a little thickness to each cross section, and that thickness is, that thickness is dx, right? And really, if you want to think about the solid of our revolution, you could think of that as a sum of solids of these cylinders, if you will. And these delta x's, these little delta x's, as we put in more of these disks, the delta x's approach dx's, right? And so these kind of solid cylinders then become these circular subintervals. Once again, the whole idea of infinite subintervals between an interval of A to B, right? Infinite subintervals, creating a situation where delta x approaches dx and your cross section, right, Now this is going to be a little bit deep. Your cross section kind of losing a dimension here, right? Each interval of a cylinder, the cross section becomes a circle. Back to Riemann's sum, right? Each of these rectangular cross sections becoming a line, right? As the behavior delta x approaches 0, geometrically, spatially, you can start to visualize the shape of those subintervals as one dimension removed, okay? Now that last part about the dimensionality is a little bit deeper than I wanted to go, but hopefully that all made the story make sense. I really loved this. I remember when I made that connection back in the day of the caveman, it was kind of a big mind-blowing moment. Like this whole integral thing started to really, really make sense and become really beautiful. Okay? All right, let's move on. Next question, everybody. Please go ahead and, well, I'll meet you in a minute. Please sketch the curve. Let's see, what should we do? It's an interesting one. Let's do the curve y equals square root of x. Graph y equals square root of x. And I'd like you to graph y equals square root of x. Let's just graph it only in quadrant 1. Well, actually, it only exists in quadrant 1. My gosh, that was just blasphemy. Y equals root x. And then I want you to shade the region between y equals root x, the y-axis, and y equals 4. So let's see. Between y equals root x, the y-axis, and y equals 4. Oh, some of you already can see where I'm going. Okay, let's shade the region. Here is the region. Shade it up, shade it up, shade it up. Da, 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 da. Okay, and here's the revolution, everyone. We're going to revolve this region. Remember, again, I'm revolving an area. I'm not revolving a curve. Revolve about the y-axis. We're going to revolve about the y-axis. Now, I'm going to meet you where we try and take a pencil and we sketch what this solid looks like. Okay, when I'm sketching this, I've got something like this. Okay, when I sketch that region, I've got this kind of thing going on, right? And maybe you're feeling your inner Picasso right now, but maybe you'll do a little shading here, okay? And what I want to ask you is, what is the cross-sectional shape? And hopefully you're saying, well, we only talked about one cross-sectional shape, and it's the circular or the disc cross-section. But in this case, though, I think you'd agree when I say that the circular cross-sections, interestingly, are stacked this way. I'm going to draw a few. They're stacked like this, right? Very excited. Oh no, look at that last cross-section I made. It looks so lopsided. Oh well, that's okay. And I'm going to just pick one of those cross-sections to emphasize. And emphasize meaning I'm going to kind of draw in the critical body parts. Let's see. Here's the center. And what did Miss Yam say? Oh, right. She said to draw the critical body parts to the original function, not its rotational image. I'm just going to do this. There's the radius, right? And maybe if you feel compelled, you'll kind of go back to the other one up here and make it look appropriate. That is my radius. Notice the difference, everyone. The radius here is a horizontal distance. Very interesting. Okay. Well, let's see. I'm going to ask you a question, everyone. Follow my question. If I'm looking at these cross-sections, these circular cross-sections seem to be stacked vertically on top of one another. Up here, these circular cross-sections were stacked horizontally. Okay? These vertical cross-sections, these cross-sections were stacked horizontally over an interval of x. These cross-sections over here are stacked vertically over an interval of y. Why am I emphasizing that? Because the interval over which your cross sections are stacked is precisely the interval of integration. So let's go back here. You ready? I am looking at an integral over an interval from 0 to 4. But this interval is an interval in terms of what? X or Y. It is an interval in terms of Y. That means my dummy here is going to be dy. Okay? What about the integrand? Well, the integrand we know is the area of one of these cross sections. It is the area of one of these disk cross sections. Well, let's see. The area of the disk cross section has to be in terms of Y, because my dummy is Y and my interval is Y. And if I know this radius length is horizontal, it's going to behoove me to express this function in terms of x. X equals y squared. So now I have a varying distance x. X equals y squared. X equals y squared. And the area of one of these disks, we know in general, this is pi r squared. In this case, it's going to equal pi. R is now right here. Y squared squared. And what I have now is my integrand. Beautifully done. Definite integral from 0 to 4. I always kind of pull the constant through, and you do too, just because it'll just make your life easier as you proceed then through the fundamental theorem of calculus. And this, here we have the volume of that solid. Okay, so as we see, and I've been kind of giving hints all along, this dummy is not so dumb. The dummy really tells you a lot. Now we have a new role for the dummy. The dummy tells you an orientation of a solid of revolutions cross sections. How lovely. Okay, everyone, that is the lesson for the day. What I'm going to do now is let you go and start the homework, okay? So the homework, as you can imagine, is going to be on solids of revolution. And the only cross-section we have so far are disks. Let me know tomorrow when I see you how this screencast went, or let me know now. It's up to you. You can even send me a quick email and say, thumbs up, Miss Yam, Oscar worthy, Oscar nomination worthy, or thumbs down, you went on some bizarre tangents. And how about a big thank you to Mr. Fullars as well. All right. Thanks, everyone. Goodbye.